Hey everyone, let's start with something fun. Have you ever heard that wah wah sound when two people hum almost the same note but not exactly? Or when two tuning forks sound together and you hear the tone rise and fall repeatedly? That rhythmic variation in loudness, it's not magic, it's physics. We call it beats. Now, what's actually happening? When two sound waves with slightly different frequencies travel in the same direction, they meet and interfere. Sometimes they strengthen each other, that's when it sounds loud, and sometimes they cancel each other, that's when it becomes soft. This periodic rise and fall in loudness is what your ear detects as beats. And if both waves have exactly the same frequency, no difference at all, your ear hears a steady tone. So, beats are nature's way of letting you hear interference in action. Alright, let's add a little mathematics behind this beautiful effect. Suppose we have two sound waves, y1 equals a sine of 2 pi f1t and y2 equals a sine of 2 pi f2t. When both waves travel together, their displacements add up. So the total displacement is y equals y1 plus y2. Now, using the trigonometric identity, sine a plus sine b equals to sine of open bracket a plus b over 2 close bracket multiplied by cosine of open bracket a minus b over 2 close bracket. Applying this, we get y equals to a cosine of pi into f1 minus f2 times t multiplied by sine of 2 pi into f1 plus f2 times t divided by 2. The sine term represents the rapid oscillations, the actual note we hear. The cosine term controls the variation in loudness. It acts as an envelope, making the sound grow louder and softer periodically. This periodic rise and fall in intensity produces the characteristic pattern of beats. Now, how often do these beats occur? That depends entirely on how different the two frequencies are. The beat frequency, denoted as f sub a, is equal to the absolute difference between the two frequencies. So, f sub b equals the absolute value of f1 minus f2. For example, if one tuning fork vibrates at 256 Hz and the other at 260 Hz, then the beat frequency becomes 4 beats per second. This means you will hear 4 cycles of loud and soft sound every second. And if you adjust one of the tuning forks until the beats disappear, congratulations, both tuning forks are now perfectly in tune. So when exactly can you hear beats clearly? Well, our ears can only distinguish loudness variations if the frequency difference is small, typically less than 10 Hz. The two waves must also have nearly equal amplitudes, otherwise, one sound just dominates the other. And they should be coherent, meaning their phase relationship remains steady, not jumping around randomly. If the frequency gap is too big, your brain stops hearing beats and starts hearing two separate notes. That's why tuning a guitar or violin works best when the two strings are almost in tune. You can actually hear the beats fade away as you reach perfect harmony. Time for the derivation. Let's walk through it step by step. We start with two waves, y1 equals a sine of 2 pi f1t and y2 equals a sine of 2 pi f2t. When we add them, the resultant becomes y equals to a cosine of pi times bracket f1 minus f2 bracket times t multiplied by sine of 2 pi times bracket f1 plus f2 bracket times t divided by 2. Now, this equation tells us something powerful. The cosine term controls how the amplitude changes with time. The amplitude swings between plus 2a and minus 2a, and it completes one full cycle when the argument of the cosine changes by 2 pi. So, the number of times the loudness reaches a maximum in 1 second is equal to f1 minus f2. This is the beat frequency. That's how we arrive at the simple and elegant relation f sub b equals the absolute value of f1 minus f2. Let's bring it to real life. Beats aren't just a classroom curiosity, they're actually a very useful tool. Musicians use beats to tune instruments. When two strings play together, the beats fade away as they reach the same frequency, a perfect tune. In physics labs, beats are used to measure unknown frequencies by comparing them with a standard source. Engineers use the same idea in radio technology, combining two signals to produce beat frequencies for detecting or mixing signals. And in the ultrasonic world, beat frequencies help find material flows using sound interference. So yes, even your radio, your guitar, and your ultrasound machine speak the same language, the language of beats. Let's wrap up this melodious concept. Beats happen when two waves of nearly equal frequencies interfere. Their superposition creates alternating constructive and destructive interference, loud, then soft, then loud again. The formula we derived, F sub B equals the absolute value of F1 minus F2, tells us how many such cycles occur per second. To hear beats clearly, frequencies must be close, amplitudes similar, and coherence maintained. From tuning forks to musical instruments, from acoustics to electronics, beats are the heartbeat of wave interference. So next time you hear that wah wah pattern while tuning a guitar or humming with a friend, smile, you're literally listening to physics in action. I hope this made beats crystal clear and maybe even a bit musical. See you in the next session where waves will bring yet another symphony of science to life.